Welcome to the today's tutorial. Today we are going to discuss about the definite integration and fundamental theorem of calculus. First thing is that understanding the definite integration. The definite integration is given by a to b f of x dx. So here we know that the indefinite integration is given as f of x dx, which is equal f of x plus c, where fx is antiderivative of f of x. Now here we will discuss about the definite integration, and this is the lower limit, b is equal upper limit. So how we'll solve this integration and how the indefinite integrations will help us to solve the definite integration. So properties of the definite integration we'll discuss here. First properties is about the order of the limit. So a to b f of x dx, if it is given, and if we need to change the order of the limit of the integration, so we need to put a minus b to a f of x dx. The second property is addition and subtraction of two functions. Suppose a to b f of x plus or minus g of x dx, which will be same as a to b f of x dx plus or minus a to b g of x dx. Third property is the additive properties. So sometimes we need to break the integration into two parts, and this rules is helpful for that. A to b f of x dx can be written as a to c f of x c to b f of x dx, where c is a any middle point between a and b. The fourth is the constant multiply a to b k of f of x dx. In this case we can take out the k and we'll have a to b f of x dx. And the fifth is a to a f of x dx, which will be 0. Next is the fundamental theorem, part 1 of calculus. So this theorem states as if f is continuous on closed interval ab and a capital Fx is defined as integration a to x f of t dt, which is also continuous on ab and differentiable on the open interval ab, and the derivative of fx is given as d dx of a to x f of t dt, which is equal f of x. Here need to be noticed that the lower limit is a constant number, upper limit is the variable, same of these functions, then derivative of this capital Fx is same as the integrand, the function which we are doing the integration will be same. So these are the 2 points we need to remember it. The lower limit of the definiteness should be constant. If it is not, means if the upper one is constant, lower one is the variable, we know how to change it using the properties of the definite integral. So the upper limit is either the variable or a function of the constant variable. If upper limit is a function, means if it is not x, is some function of x, then we have to find the derivative is like this: f dash x is equal to dx a to gx f of dt. So it will be f of gx and then derivative of g. Now we will apply the fundamental theorem 1 and we will solve this problem. Find f dash x if fx is equal to 3 to x sine 3t dt. So it's simple by directly. So f dash x is equal x. That's all. Now in this case, here you have instead of x, it's x squared. So look on the difference between these two problem. Here it is x, here it is x squared. That means function of x. So in this case, we have to do one step more. F dash x, this is equal d dx of 3 to x squared sine 3t dt, which is equal sine to the power 3 x squared and the derivative of x squared. So which is equal 2x sine to the power 3 x squared. That's all. Now we have another problem where you have the upper limit is constant, lower limit is function of x. So in this case, before solving the derivative, we need to rewrite it, because in our standard form we must have the lower limit is constant and upper limit is variable or function of the variable. So it can be written as minus 3 to e to the power x sine 3t dt. So this implies the fundamental theorem f dash x is equal minus, as it is, sine power 3 e to the power x and then derivative of e to the power x, which is equal minus e to the power x sine 3 e to the power x. Now in this problem we have both limit are variable x square and x to the power 3. This problem can be solved by two methods. One is we can write this y as, say, x square to 0 dt plus 0 to x to the power 3 dt. So this can be written as minus 0 to x square 3t dt plus 0 to x to the power 3. Now we'll apply the fundamental theorem. So dy dx is equal minus sine 3 x square derivative of x square plus sine 3 x cube plus derivative of x cube. So which is equal minus 2x sine 3x square plus 3x square sine 3x to the power 3. This method can be summarized as, whenever you have, like, say, y is equal gx hx f of t dt, then dy dx we can have f of hx h dash x minus f of gx g dash x. So in this case, this is equal sine 3 x to the power 3 derivative of x to the power 3 minus sine power 3 x square derivative of x square. So this is equal 3x square x to the power 3 minus 2x sine 3 x square. So both the way answer are same. Now next one is dy dx from y equals 2 tan x to 0 1 over 4 plus t square dt. So again in this case we need to reverse the order of the limit. So y is equal minus 0 to 2 tan x 1 over 4 plus t square by fundamental theorem. This implies dy dx is equal minus 1 over 4 plus 2 tan x whole square, then ddx of 2 tan x. So this is equal minus 2 secant square x, this will be 4 plus 4 tan square x. So this is equal minus 2 over 4 secant square x over secant square x. Here we are using 1 plus tan square x is equal secant square x, and here we are using derivative of tan x is equal secant square x. This is equal minus half. The last problem on this section is y equal 1, y is equal 3 to the power x 1 ln t. So again we have to write it first. Y is equal minus 1 3 to the power x ln t dt. So dy dx, this is equal minus ln of 3 to the power x derivative of 3 to the power x. So this is equal minus x, and derivative of 3 to the power x is 3 to the power x ln 3. Next we have fundamental theorem 2 of calculus. So in this case we have exactly the idea that how we will do the definite integration. So you'll see that if f is continuous and fx is an antiderivative, so for this, to apply this theorem, we must know the antiderivative of the given function. Then we'll have a to b f of x dx is equal f of b minus f of a. We'll do more example, but let's have the simple example. Suppose 1 to 2 x dx. So we know that the antiderivative of x to the power m is x to the power m plus 1 over m plus 1. M is not equal minus 1. So in this case m is equal 1. So we'll have the antiderivative is x square over 2, and the limit is 1 to 2. So this is equal upper limit, so 2 square over 2. So this is f of b minus f of a. So this is 1 over 2. So this is equal 2 minus half. So this is 3 over 2. So therefore the integration to use the fundamental theorem part 2, you should know the antiderivative of the function. So now we will consider different problems, and for this part at this moment you should know the antiderivative of each of the functions, then you can solve it. So first problem is we have x square dx. So in this case the antiderivative is x to the power 3 over 3 and limit is 0 to 4. So upper limit 4 to the power 3 over 3 minus 0. That means 64 over 3. This is the answer. So for the definite integral there will be no constant c and the answer will be always numerical number. Now antiderivative of sine 2x. So we know that ddx of cosine 2x over 2 minus is equal sine 2x. So therefore the integration is minus cosine 2x over 2, limit is 0 to pi. So this is equal, take out the minus half first and then 0 to 2x, 0 to pi. So this is minus half cosine 2 pi minus cosine 0. So this is equal minus half cosine 2 pi is 1, cosine 0 is 1. So the answer is 0. Next is 0 to 1, 3 d theta over 1 plus theta square. So 3 is a constant we can take out, and then you have 0 to 1 d theta over 1 plus theta square. We know that d theta of tan inverse theta is equal 1 over 1 plus theta square. So this is equal 3 tan inverse theta, limit is 0 to 1. So therefore this 3 tan inverse of 1 minus tan inverse 0. So this is 3 pi over 4 minus 0. So the answer is 3 pi over 4. This problem you can do either separate them as a two function or two integration, or you can do it together. I will prefer to do it together. So the first one is 6 and dt, so it will be 6t minus t, the antiderivative will be t square over 2, so it will be 1 over 6 t square, limit is minus 4 to 2. So I will put the 2 first, so it will be 12 minus 4 over 6, then minus 24, and then minus 16. So 12 plus 24, so 36, and minus 4 over 6 plus 16 over 6, so it will be plus 12 over 6, so that means 2. So this answer is 38. Here again you can do separately or you can do togetherly, so I'll prefer to do together. So 3x square, so it will be 3 x to the power 3 over 3 minus 2 x square over 2 plus 4x, limit is minus 1 to 1. So this is x to the power 3 minus x square plus 4x minus 1 to 1. So this is 1 minus 1 plus 4 minus minus 1 minus 1 minus 4. So this is equal 4. This is minus plus 6. So this is equal 10. It is 1 to the 1 to 64 x to the power minus 7 over 6. So again here x to the power m, antiderivative is x to the power m plus 1 over m plus 1 for m is not equal minus 1. So I'll use that. So it will be x to the power minus 7 over 6 plus 1. So which will be minus 1 over 6. So x to the power minus 1 over 6 minus 1 over 6 1 to 64. So this is equal minus 6 64 to the power minus 1 over 6 minus 1. So this is equal minus 6 64 to the power minus 1 over 6. So 64 is equal 2 to the power 6. So 64 to the power minus 1 over 6 is 2 to the power minus 1. So this is equal half minus 1. So which is equal 3. Next problem is 0 to 2 pi 1 plus cosine x over 2 dx. So here we can do it like this. Antiderivative of dx is equal x plus sine x over 2 over half 0 to 2 pi. So this is equal x plus 2 sine x over 2 0 to 2 pi. So we'll first put the limit 2 pi. So 2 pi plus 2 sine 2 pi over 2 minus 0 plus 2 sine 0. So it will be 0. So this is 2 pi plus 2 sine pi. So this is equal 2 pi. So to solve this problem, let's recall d theta of secant theta is equal secant theta tan theta. So therefore, for this function, the antiderivative is secant 2u over secant 2u over 2, and the limit is 0 to pi over 6. So this is equal half secant pi over 3 minus secant 0. So this is equal half secant pi over 3 half secant pi over 3 is 2 minus secant 0 is 1. So therefore the answer is half.